Alright, so this is my Lab 4 report on mapping electric fields. The main goal of this lab was to map electric fields by sketching out equipotential lines and using them to determine the direction and configuration of electric field lines. And then we used those sketches to compare the different kinds of electric fields that were created by different electrode configurations, because we had two main different electrode configurations that we were looking at. So what we did is, in the pre-lab, we started by using an online simulation to observe different charges, electric field lines that went with those charges, as well as equipotential lines. And using that, we were able to determine that equipotential lines are always perpendicular to electric field lines, and equipotential lines never crossed over each other. And I'll show you an example of that in a moment. And then we used a setup in lab and ran some current, or however it's said, through I think it's like a carbon sheet or something like that. And there were, like I mentioned before, two different electrode configurations. One of them was like two parallel plates, and one of them was like a dipole, and I'll show you both of those in a moment. And using those, we used the plates first. We then used the galvanometer to locate the equipotential lines on the sheet, and then we sketched it out on another piece of paper. We then went back to an online simulation and basically recreated what we did on the sheet in the simulation. But this time we got a little bit more technical with it and ran some calculations to find out the strength of the electric field at different locations. And we ended up going back and doing another hand sketch of the dipole electrode configuration. Okay, so here we have two different setups in the online simulation. On the left there, we just have a single positive point charge. So the red dot in the middle with the plus on it, that's the charge. The green lines are the equipotential lines, and the white arrows are the electric field lines. So as you can see from this, the electric field lines are always perpendicular to the equipotential lines, and no matter how close you get down there in the center towards the middle, the equipotential lines never crossed each other. Also, we can tell from this that the closer you get to the charge, the stronger and stronger the electric field is getting. Like, for instance, on the very far outside of the sketch, the furthest away green line, that's around 5 volts. Then it goes down to 10, 15, 20, 25, 30, 35, and around 45 volts. And you can see the lines are getting closer and closer together as you get further towards the charge. Now on the right here, we have a positive and a negative charge, and right off you can tell from the electric field lines that they are being repelled. They're pointing away from the positive charge and are pointing towards the negative charge. And what's unique is that they actually start to curve away from the positive and towards the negative. That's why you have the cool looking shapes there. And then with the equipotential lines, you can see that they aren't exactly circular like they were with the point charge on the left. So we have an equipotential line at 15 volts, 10 volts, 5 volts, 0 volts, which is that straight line in the middle, and then negative 15, negative 10, and negative 5. And what's unique is that you can actually see that, let's take the positive charge for example, the further left you go, the actual equipotential line begins to bulge away, and that is due to the electric field remaining stronger and not being reduced by the impacts of the negative charge like it does on the right. Now here we were just told to make up a random one of our own will, so I just made this simple positive charge in the center with a sort of ring-like structure of negative charges around it, and that there's some extra positive charges in there as well. And you can see that even in this example, the equipotential lines do not cross, and everywhere you look, if you pay attention, the equipotential lines are also always perpendicular to the electric field lines. These are the two hand sketches we did. You see the one on the left there is the dipole, the one on the right is the two parallel plates. The more horizontal lines on both of these hand sketches are the equipotential lines, and then the more vertical lines that have the arrows on them point away from the positive and towards the negative, and you can see how they curve from the positive towards the negative on both examples. This is the online simulation of the parallel plates that we did in class, and this is the one that we actually did the calculations with. So you can see how we have the different strengths of the equipotential lines. We have a positive row on the left and a negative row on the right. And you can see how they go from positive charges on the left, reaching down to close to zero, and then go back up to, down to negative charges on the right. These are the table showing the results. So we have from the lines of 80 volts to 70 volts. In between those, what we did is we took the two charges and we subtract them, and then we divided them by the distance between the two, and that gave us the strength of the electric field between those two lines. And you can see the further you get to the middle, the lower it goes. Then when you start going back to the even further over towards the negative charge, the actual strength of the electric field increases more. So all in all, we did accomplish the original goal of mapping the electric fields given off by different configurations, electrode configurations, using equipotential lines, and then we compared the similarities and differences between the different electrode configurations. This goal was accomplished using the help of online simulations as well as hand-drawn sketches of the equipotential lines. So yeah, that's about it.